At the center of this model is a neurochemical known simply as substance P. Substance P is believed to act as a neurotransmitter, passing pain information from the peripheral nerves to the neurons of the brain. The more substance P released, the more intense the pain. Researchers believe that the natural opiates may bind with substance P-containing neurons and inhibit the release of substance P. In other words, the natural opiates achieve pain reduction by inhibiting the effectiveness of substance P. In light of this model, the ancient Chinese method of controlling pain through acupuncture is finally beginning to make sense to Western scientists. It may very well be that the needles used in acupuncture somehow stimulate the release of natural opiates, which in turn inhibit the release of substance P. While the discovery of natural opiates represents a major breakthrough in understanding the brain, most researchers believe it is only the first of many more advances in this area. It may be that the brain produces a whole range of mind-altering chemicals, from stimulants to hallucinogens. There is already reason to believe that the brain produces its own tranquilizer. Although a specific substance has yet to be identified, researchers believe it may be quite similar to a synthetic anti-anxiety drug known as Valium. Since its discovery in the early 1960s, Valium has been widely prescribed for moderate to severe anxiety. Although it was initially believed to be a non-addictive and relatively safe drug, new evidence regarding the action of Valium in the brain has challenged this view. As with opiates, Valium molecules readily bind with specific receptor sites throughout the brain. These receptor sites are most prevalent in the part of the brain known as the limbic region, which is responsible for the regulation of emotions. According to recent studies, the binding of Valium molecules triggers the release of an inhibitory neurotransmitter known as GABA. This increase in GABA molecules depresses neural activity in the limbic region. When the limbic region is depressed, a person feels removed from the stimuli which would normally produce tension and stress. This explains why Valium has been nicknamed the I don't care drug. To most neuroscientists, the fact that the brain contains Valium receptor sites is proof that the brain also contains natural tranquilizers, which bind to these sites. Most feel it is just a matter of time before such chemicals are identified. In the meantime, new drugs are being developed which may act in greater harmony with the brain than does Valium. These new drugs may relieve anxiety more efficiently than Valium without the possibility of addiction or other serious side effects.
Another common drug which depresses the central nervous system is alcohol. Although often thought of as a recreational drug, alcohol is frequently used as a quick means of reducing anxiety. The precise action of alcohol on the brain is as yet unknown. It does appear, however, that the drug somehow affects the entire neural membrane, slowing down the activity of the neurons. While alcohol is definitely a depressant drug, it can at times appear to stimulate rather than depress activity. We have all known people who are more outgoing, talkative, and energetic when they have been drinking. This is because alcohol depresses the part of the brain that controls our inhibitions. How a person behaves when he is drunk depends largely on what behavior he inhibits when he is sober. When alcohol is consumed regularly in large amounts over a period of years, it is addictive and has been related to a variety of serious diseases. Although the neurological component of alcoholism is not well understood, recent studies show that chronic use of alcohol can actually cause structural changes in the brain. While the psychoactive agents discussed so far work by depressing the central nervous system, another category of drugs has the opposite effect. These drugs stimulate activity in the brain and nervous system. We will discuss two types of stimulants, caffeine and amphetamines. Caffeine is a mild stimulant belonging to a class of drugs known as xanthines. Although the xanthines are the oldest type of stimulant known to man, it is only recently that the action of caffeine on the brain has been understood. We now know that caffeine works by countering the effect of a naturally occurring chemical known as adenosine. The function of adenosine is to inhibit the release of certain neurotransmitters throughout the brain. By interfering with this inhibitory function, caffeine causes an increase of neural firing and an overall stimulation of the nervous system.
Another group of stimulants, known as amphetamines, were developed in a laboratory over 50 years ago. These drugs are more powerful than caffeine, and their action upon the central nervous system is also quite different. Structurally, amphetamines are similar to the norepinephrine and dopamine neurotransmitters. For this reason, scientists once believed that amphetamines produce their effect by simply binding with available receptor sites and stimulating the neurons to fire. According to current research, however, the mechanism by which amphetamines stimulate the brain is more complex than once believed. It now appears that amphetamines work in two stages. First, they cause the release of neurotransmitters into the synapse. Second, they block the reuptake of these very same neurotransmitters, making more of the chemicals available to bind with neighboring neurons. Since the neurotransmitters involved tend to stimulate neural firing, the increase of these chemicals in the synapses of the brain can have a profound effect on behavior. The person using amphetamines feels alert, aroused, and ready to go, even though there are no external factors requiring this response. Incidentally, one of the major side effects of amphetamines is a reduction of appetite. With hundreds of thousands of overweight Americans struggling to shed extra pounds, it's no wonder this aspect of amphetamine use was received with enthusiasm. Over 90% of the amphetamines produced in this country are prescribed for weight reduction purposes. Unfortunately, there is no reason to believe that amphetamines actually help in long-term weight loss. The appetite-reducing effects of the drug are short-lived, and once a person stops taking it, lost pounds return quickly. Another common yet seemingly paradoxical use of amphetamine-like compounds is in the treatment of hyperactive children. Without medication, the typical hyperactive child displays increased and inappropriate motor activity, aggression toward peers, and an inability to concentrate. When given stimulants, however, the child slows down considerably, and his level of concentration increases. How can a drug which has such a stimulating effect on adults exert such a calming influence on hyperactive children? Aren't these effects paradoxical? Dr. Gerald Brown, a researcher at the National Institute of Mental Health and a practicing child psychiatrist, explains.
Why children might get a somewhat different effect from amphetamine than adults is really not known. So also some more recent studies have shown that grown-ups who were hyperactive as children still seem to get a calming effect as opposed to adults who are not hyperactive as children. So this tends to indicate that probably these paradoxical effects, in quotes, may be related to there being some basic biochemical difference between hyperactivity at any age versus people who are not hyperactive.
We have come quite far from the days when neuroscientists believed that the brain was a continuous network of electrical fibers. Who could have guessed that the tiny gap between neurons, which so baffled scientists, would prove to be so vital to human perception, feeling, and behavior? Yet, even with the great strides we have made in understanding the brain, the most knowledgeable of scientists must be humbled by how little we really know. Dr. Bunny.
Now, it's obvious that we've acquired an exponential increase in our knowledge in the last 20 years concerning how the brain functions. But in my view, this is just the tip of an iceberg at this point. We have an incredible amount to learn further about this complex organ in the human body.